In 2021, one container ship blocked the Suez Canal for 6 days, freezing $9.6 billion in daily trade. Everything stopped. 800 years ago, a nomadic empire with no factories, no cities, and no electrical grid managed a logistics network that spanned 12 million square miles. And it never skipped a beat. The modern system is built for speed, stripped of every buffer and reserve. That makes it fast, but it also makes it fragile. One shock and it breaks. The Mongols built the exact opposite, a system of high redundancy, decentralized nodes that thrived on the chaos that shuts us down today. We're deconstructing 15 of their innovations, from mobile manufacturing to peer-enforced accountability, that solve problems modern logistics still gets wrong. The final one, a rotation matrix for imperial security, is a strategy corporations have spent decades trying to copy, but haven't yet cracked. The first innovation starts with a rider, a fresh horse, and a relay network that changed the physics of information forever. 4 innovations, one idea behind all of them. Build a system that cannot be stopped by destroying any single part of it. The first modular logistics network. In the winter of 1241, a Mongol courier left Karakoram carrying an imperial decree. He did not stop to rest. He did not slow for weather. He did not wait for a fresh horse, because a fresh horse was already waiting exactly 25 miles ahead, and 25 miles after that, all the way to the edge of the known world. This was the Örtöö. The engineering behind it was deliberate. 25 to 30 miles is the physical limit of a horse at a continuous gallop. The Mongols measured that limit and built their entire communication network around it. Every station sat at that exact interval, each one stocked with fresh horses, standardized rations, and secure quarters for the incoming rider. At its peak, the system in East Asia alone ran more than 1,400 stations, 44,293 horses, 8,889 oxen, thousands of transport carts. Here is the part worth sitting with. If a single station was destroyed by weather, rebellion, or resource failure, the courier bypassed it. He rerouted to the next node and kept moving. The network did not halt. It simply rerouted. Modern hub and spoke logistics does the opposite. It piles volume into massive centralized sorting facilities. When one goes down, an ice storm in Memphis, a labor strike in Los Angeles, the downstream chain stalls. There is no bypass. There is no adjacent node. There is only a queue. The Örtöö held 125 miles per day for 150 years without a single technological upgrade. The principle that made it work was not speed. It was redundancy baked into the architecture itself. Security, authorization, and resource access in one object. Every modern logistics network has a friction problem. Customs clearance, port authority approvals, multi-agency sign-offs. A shipment moving from Shanghai to Chicago passes through dozens of jurisdictional checkpoints, each one a potential delay, each one a potential failure point. The Mongols solved this in the 13th century with a piece of metal worn on a belt. The Paiza, also called the Ger-Tereg, was a tiered tablet carried by couriers and imperial officials. The material told you everything about the bearer's authority. Gold tablets with a tiger's head design meant the highest-ranking commanders. Plain silver or bronze identified lower-tier envoys. Rank was visible, immediate, and universally understood across the entire empire. The inscription on the highest-tier tablets, written in the Fagspar script, left no room for interpretation. By the strength of eternal heaven, an edict of the emperor, he who has no respect shall be punished, shall die. Under that authority, any civilian, merchant, or local official along the route was legally required to supply the bearer with fresh horses, food, and armed escorts on the spot. No application, no waiting period, no negotiation. A courier carrying a gold Paiza did not ask for resources. He took them, and the consequence of refusal was death. Modern logistics spends billions annually managing the friction that one piece of engraved metal eliminated. The insight is not the object itself. It is the design principle behind it. authority and access integrated into a single credential that every node in the network recognizes without question. The first continental paper economy. Hauling money across a continent is a logistics problem. Before the Yuan dynasty, long-distance trade across Eurasia meant physically transporting copper cash or silver, heavy, bulky, and a target for every bandit between Persia and China. A merchant moving goods across that distance was also moving a small fortune in raw metal, which meant he needed guards, which meant he needed more money to pay the guards. The problem compounded at every stage. Kublai Khan's answer was the Chao, the first paper currency designed as the sole circulating medium of a continental economy. The mechanism was precise. The currency was backed not by stored precious metals, but by the absolute authority of the state and its monopoly over critical commodities, primarily salt. To force adoption, the Yuan government made trading in gold, silver or copper coins illegal. Merchants were required to exchange their bullion for Chao paper notes at the Imperial Mint. The denomination system was built for scale. Copper-denominated notes handled small local transactions. Silver-denominated notes handled large, long-distance trade. A merchant could now cross 3,000 miles carrying a leather satchel of paper instead of a cart of metal. That separated currency from physical metallic limits and created a liquid, portable medium of exchange that funded massive infrastructure projects and stabilized market prices across continents, centuries before modern central banking existed. But the system had a structural flaw, and this channel will not pretend otherwise. Under fiscal pressure, civil wars, military campaigns, imperial court spending, the Yuan government began printing currency without the commodity backing to support it. As fiscal pressure mounted from endless military campaigns and massive court spending, the Yuan government abandoned all pretense of commodity backing and resorted to aggressive overprinting. The currency lost its credibility, eventually requiring cartloads of notes for basic daily transactions. An early case study in how liquidity becomes worthless once the political will to maintain fiscal discipline vanishes. The population abandoned it and went back to barter. The Chao was a brilliant system until fiscal discipline broke. That tension between monetary liquidity and the political will to maintain its backing is not a 13th century problem. It is the central problem of every central bank operating today. The first joint stock trade insurance system. A single merchant crossing the Silk Road in the 13th century faced a simple calculation. One bandit attack, one sandstorm, one collapsed bridge. Any of those events meant total financial ruin. That risk was the primary reason individual traders avoided the long routes entirely, which kept the routes thin, the goods scarce, and the prices high. The Mongols solved this with the Örtöö, a network of state-sponsored merchant associations that functioned as a mutual insurance pool. Merchants pooled their capital, labour and transport into a single joint stock caravan. Any losses, stolen goods, dead animals, destroyed cargo, were distributed proportionally across the group. No single trader could be wiped out by one event. The state backed it further. Ortogh members received low-interest imperial loans, protected passage along the Örtöö grid, and full exemption from transit taxes, the heavy tolls that traditional dynasties used to extract revenue from every caravan that crossed their territory. The result was a transformation. The Silk Road went from a series of disconnected, high-cost regional corridors to a unified, low-friction continental trade network. The empire profited from the activity, not the taxation of it. Small logistics operators today face this same problem every day. One catastrophic event, and they are finished. Large platform operators spread that same loss across their entire network and absorb it. The Örtöö solved that asymmetry in the 13th century with a pooled capital structure and state-backed risk distribution. The corporate insurance industry does the same thing today. It just charges more for it. 3 chapters still ahead. The next one is where the engineering gets physical and where the Mongols solved a problem that modern military planners still haven't cracked. Every modern military depends on a fixed supply depot. It is the one point that, if cut, stops everything. The Mongols made that vulnerability disappear entirely. Passive structural engineering at its physical limit. A modern military tent is a rigid structure. It resists wind by mass. It retains heat by trapping air in foam or fiberglass. It needs metal poles, synthetic fabric, and a team to assemble. In a sustained windstorm above 40 miles per hour, it fails. The Ger, the primary shelter of the Mongol forces, was built on entirely different principles. The skeleton is a collapsible circular wall section made from a flexible wooden trellis called the khana. The slats are joined not by nails or rigid joints, but by flexible rawhide pins. The entire frame can expand, contract, and deform slightly under stress without cracking. It absorbs force rather than fighting it. A single high tensile woven wool band wraps around the exterior circumference. When the roof poles push outward under load, that band counteracts the force and distributes the pressure evenly across the entire lattice. No single point bears the load. The whole structure shares it. The circular dome handles the wind. When lateral wind shear hits a flat vertical surface, it pushes. When it hits a circular dome, it glides around the perimeter, and the aerodynamic shape converts that lateral force into stabilizing downward pressure. The harder the wind blows, the more stable the structure becomes. Insulated with thick, water-resistant sheep's felt, the Ger holds against winds exceeding 50 miles per hour and temperature swings from -40 degrees Fahrenheit in winter to 100 degrees Fahrenheit in summer. The entire structure disassembles, loads onto one pack animal, and reassembles in under 2 hours. No metal fasteners, no synthetic materials, no power tools, and it outperforms modern rigid military tents in heat retention, wind resistance, and structural durability. Manufacturing on the move. The single greatest vulnerability of a conventional army is its supply depot. Fixed, known. The first target an adversary tries to cut off. The Mongols eliminated that vulnerability by making the depot move with the army. The Ger-Tereg were full-sized yurts permanently mounted on massive wooden wagons. Axle lengths exceeded 20 feet, built specifically to prevent tipping on uneven steppe terrain. Teams of up to 22 oxen pulled these platforms in disciplined columns across hundreds of miles. These were not storage wagons, they were functioning workshops, travelling armour fabrication facilities, mobile foundries, treasury units, command offices. Every manufacturing and administrative function that a conventional army would house in a fixed base camp was mounted on wheels and kept pace with the marching force. The wide axle was deliberate engineering. Spreading the massive weight of the structure over a broad surface area prevented the wagons from sinking into soft steppe soil. The same principle behind modern wide-track military vehicles arrived at 700 years earlier through direct observation. When the army moved, the factory moved. When the army stopped, the factory was already there. There was no supply line to cut, because the supply line was the army itself. Modern forward operating bases are still fixed, still targetable, still the first thing an adversary plans to isolate. The Mongols solved that in the 13th century with a wide axle and 22 oxen. Portable water purification without power or fire. Water security across the arid steppes and deserts of Central Asia was not a comfort issue. It was a hard survival constraint. A cavalry force that stopped to boil water lost time. A cavalry force that drank untreated water from stagnant puddles and saline wells lost men. The Mongols solved this with a single piece of leather and the physics of motion. The canteen was made from a seamless piece of rawhide, typically from the bladder or stomach of a cow or horse. The raw skin was cured in animal fats and birch bark oils, which hardened the collagen fibres and made the leather waterproof, flexible and resistant to bacterial decay. Inside, soldiers packed a layered matrix of crushed wood charcoal and fine river sand. The canteen was suspended from the saddle. As the horse moved at a trot, The rhythmic gate subjected the liquid inside to continuous mechanical agitation. That motion forced the raw water through the charcoal and sand matrix, pulling out organic impurities, neutralizing pathogens, filtering suspended sediment. The horse's movement was the pump. The charcoal was the filter. The rider drank clean water from muddy riverbanks and stagnant wells without stopping, without fire, without fuel. Portable water filtration is a $3 billion global industry today. The Mongols solved the core engineering problem in the 13th century with one piece of cured leather and the gait of a horse. Field metallurgy, without a factory. Mass-producing steel weapons, iron arrowheads and armour on the march is a problem modern military logistics has never fully solved. Armies today depend on distant industrial supply chains for weapons and equipment. Cut that chain and the army stops fighting. The Mongols built their forge wherever they stopped. The Sharton pit furnace was clay-lined and dug directly into the steppe soil. No stone masonry, no brick, no permanent structure. It measured 12 to 16 inches in height, with thin clay walls built and cured from local materials in a matter of hours. Airflow came from double-acting leather bellows made from horse hides. Internal wooden valves delivered a continuous stream of oxygen to the charcoal fire on both the push and the pull stroke. Not just the push, which is the limitation of a standard single-acting bellows. Continuous airflow meant sustained high temperature. To maximise output, the bellows were linked by wood and leather mechanical connections to horses or oxen walking in circular paths. Animal power drove the bellows. The bellows drove the temperature. The temperature reached the threshold needed to melt iron ore and forge high-carbon steel. The result? Field repair of damaged armour, smelting of captured metal, and the production of hundreds of thousands of standardised arrowheads, without any dependency on a distant industrial capital. Modern military doctrine still treats forward manufacturing as a logistical impossibility. The Mongols treated it as standard field procedure. 2 chapters down. The next one is where it gets unexpected, because the Mongols solved a problem that has killed more armies than any weapon ever built. And they solved it with leather, wind, and fermentation. 3 innovations, all of them answered the same question. How do you feed 100,000 men across 3,000 miles of desert and frozen steppe with no supply convoy, no refrigeration, and no resupply schedule? Cold wind freeze-drying before the industrial age. The Mongolian plateau in winter drops well below zero. For most of human history, that was a threat. The Mongols turned it into a food manufacturing process. Long, thin strips of raw beef or horse meat were hung under the eaves of the Ger during peak winter. What happened next was not drying. It was sublimation. Sublimation is the process by which solid ice crystals convert directly into water vapour, without passing through a liquid phase. Sub-zero temperatures combined with dry, high-velocity Arctic winds triggered this transition inside the meat's cellular structure. The water did not melt and drain away. It converted directly to vapour and dispersed into the air. Because the water never liquefied, the cellular structure of the protein stayed intact. No decay, no bacterial growth. The meat became hard and fibre-like, then was ground into a fine powder. The compression was extraordinary. An entire cow's worth of protein reduced to a volume that fit inside a single cow bladder bag. A soldier carried that bag. In the field, he added boiling water and had a full protein meal in minutes. Modern military MREs weigh roughly 1.5 pounds per meal and last 3 years under controlled storage conditions. Borts delivered equivalent protein at a fraction of the weight and lasted years with no packaging, no preservatives, and no refrigeration. The Mongolian winter did the work. Physics did the rest. The horse as pasteurizer. Hauling grain sacks across a continent is slow. Driving livestock herds with a cavalry force is slower. The Mongols needed a high-calorie, lightweight, shelf-stable food source a mounted soldier could carry and consume without stopping. They built one from milk. Fresh mare's or cow's milk was boiled to eliminate pathogens and reduce water content. The cream paste was skimmed off. The remaining skim milk was spread on flat wooden boards and left in direct sunlight until it dehydrated into dry, stable crystals. Each soldier carried roughly 10 pounds of this dried milk paste in a leather saddle flask. Every morning, he added water to the flask and sealed it. Then the horse went to work. The continuous motion of the horse's trot acted as a mechanical mixer, the rhythmic movement rapidly blending the dried crystals back into the water. At the same time, the friction and body heat from the horse's flank kept the flask at a mild temperature, passively warming and pasteurizing the mixture as it reconstituted. By midday, the soldier had a warm, calorie-dense liquid meal, produced entirely by the horse's own movement and body heat. No fire, no fuel, no halt in the march. The horse was simultaneously the transport vehicle, the blender, the pasteurizer, and the warming plate. That is not a coincidence. That is engineering. Biochemical scurvy prevention without citrus or agriculture. Scurvy killed sailors, soldiers, and explorers for centuries. The British Navy lost more men to it than to combat in some campaigns. The cause is straightforward: severe vitamin C deficiency. The solution, once identified, was citrus fruit. But citrus requires agriculture, fixed supply chains, and a climate the Mongolian steppe does not provide. The Mongols avoided the scurvy outbreaks that crippled later European armies by maintaining a radical, high-density nutritional cycle. Their diet relied on a continuous intake of fresh blood and nutrient-dense organ meats. The liver and spleen are exceptionally rich in vitamin C, combined with the active probiotic and vitamin-rich profiles of fermented mare's milk, known as Örtöö. This combination provided a complete, bioavailable supply of ascorbic acid that kept the army functioning without a need for vegetable cultivation or citrus. One chapter left. These final four are not about keeping men alive. They are about keeping an empire from tearing itself apart, at scale, across distance, without a single radio, satellite, or digital network. Ancient materials science at its physical limit. Modern carbon fibre recurve bow are precision instruments. By one critical measure, they are still outperformed by a weapon built in the 13th century from horn, sinew, wood and fish bladder glue. The Mongol composite recurve bow was built from 4 distinct layers laminated together in a precise sequence. The horn belly faced the archer, placed on the compression side of the box, the side that compresses under draw. Horn resists compressive force without cracking. The wood or bamboo core formed the structural frame. The sinew back faced the target, applied in layers on the tension side, the side that stretches under draw. Sinew has extraordinary tensile strength, stretching significantly before snapping back with stored energy. The rigid CR ears, wooden extensions at each end, acted as mechanical levers. At the end of the draw stroke, these levers reduced the required pull force, preventing the stacking effect that makes high draw weight bow difficult to hold at full draw. A mounted archer could hold a 160-pound draw weight buoy long enough to aim. The asymmetrical design was the final refinement. The lower limb was built slightly shorter than the upper. That allowed the archer to swing the bow clean across the horse's neck without striking the saddle. Built specifically for 360-degree mounted combat. The binding agent was organic glue boiled from fish bladders, and that was the vulnerability. In humid climates, the southern campaigns in Vietnam, the naval campaigns against Japan, moisture softened the glue. The laminate separated, the buoy lost its stored energy. The Mongols lost campaigns partly because of this single material failure. Modern carbon fibre bow have not exceeded the energy storage per ounce ratio of this design. They have only solved the moisture problem. The first battlefield data relay. Commanding 100,000 men across miles of dust, noise and chaos is a communications problem. Visual flags need line of sight. Human messengers need time. Voices carry perhaps 200 yards in open terrain. In the middle of a cavalry engagement, none of those systems work. The Mongols solved battlefield command transmission with aerodynamics and bone. Whistling arrowheads were made from hollow bone with precision-cut aerodynamic slots in the surface. When launched at high velocity, airflow through those slots generated distinct, high-frequency sound waves. The pitch varied by the size and geometry of the slots. Different pitches carried different commands. A high-pitched whistle commanded a specific Arban, a 10-man unit, to execute a feigned retreat. A deep, resonant whistle signalled a full 2 men, 10,000 men, to converge fire on a precise coordinate. The acoustic signal bypassed the latency and unreliability of every other command method available. A single arrow, fired into the air, transmitted a specific tactical instruction to a specific unit size across miles of battlefield noise. No messenger, no flag, no delay. The honest limitation: hollow bone made these arrows drag-heavy and structurally light. They lacked the mass to penetrate heavy plate armour. They were purely signalling devices. An archer who fired a whistling arrow was not attacking, he was communicating. Battlefield command latency is still a critical failure point in modern military doctrine. The Mongols addressed it acoustically in the 13th century. Peer accountability as structural design. Modern corporations spend billions annually on compliance infrastructure, internal audit departments, regulatory oversight bodies, performance management systems. All of it exists to solve one problem. How do you make people accountable when no one is watching? Genghis Khan solved that with mathematics and consequence. He dissolved the traditional Mongol clan structure entirely. Tribal bloodlines, family loyalties, regional affiliations, all erased. In their place, a strict deciemal command hierarchy. 10 men formed an Arban, the foundational tactical and logistical cell. 10 Arbans formed a Jargun of 100. 10 Jarguns formed a Mingan of 1,000. 10 Mingans formed a Tumen of 10,000. The accountability mechanism was enforced by the Great Yasa, the Imperial law code. If a single member of an Arban fled combat, showed cowardice, or failed a logistical task, the remaining 9 were executed. If an entire Arban fled, the parent Jargun faced decimation. Every soldier became an active inspector of every other soldier. There was no compliance department because compliance was enforced laterally, by peers, under the threat of shared consequence. The system was self-monitoring and self-correcting across thousands of miles of decentralized operations without a single bureaucratic oversight layer. Modern organizations spend enormous resources trying to build accountability from the top down. The Mongols built it from the inside out by making every node in the network responsible for the performance of every adjacent node. Accountability is not a management function. It is a structural design problem. The Arban solved it in the 13th century. Security, succession, and loyalty in one system. Every expansive empire in history has faced the same internal threat. The generals who win the wars become powerful enough to challenge the throne. The regional commanders who control distant supply chains develop independent loyalties. The empire expands until the center can no longer hold the edges. That is not a political problem. It is a systems engineering problem, and the Mongols solved it with a rotating guard shift. The Keshik was a 10,000-man elite household guard. It functioned as a decentralized hostage network. The sons and brothers of regional commanders served in the guard, ensuring that any commander considering defection knew the immediate cost of his actions. Simultaneously, this guard served as an imperial finishing school, training these elite youths in the Khan-specific administrative and logistical doctrine before they were deployed to command distant Tumens. The Keshik solved 3 distinct problems with one rotating personnel system: coup prevention, succession continuity, and leadership development. Modern corporations maintain separate departments for each, separate budgets, separate leadership, separate strategic objectives. The Keshik did all 3 with one guard rotation. The Mongols did not build redundancy into their systems. They built redundancy into their people. The Mongols didn't build an empire that ran on infrastructure. They built one that ran on physics, peer accountability, and passive chemistry. The modern grid can fail, our microchips can glitch, and our concrete can crack. But those fundamental laws of nature have not changed. We've set this knowledge aside, not because it failed, but because efficiency was more profitable than resilience. If you want to stop accepting fragility as the price of progress, subscribe to Silk Road Diaries. I'm curious, which of these 15 systems would you trust to keep your own world running when the power goes out? Let me know in the comments, and I'll see you in the next one.